Hello there, and welcome to the second last video that's going to be shared. Just a small note that there has been a slight change of plans in the perceived schedule. This is video number 5, and the 6th video is going to be a continuation of this topic of engines. So just to reiterate what we've gone over, so our first class was going over theory of flight, and then we had one class or review session on navigation. We just wrapped up 2 review sessions of meteorology, and now we have 2 engine classes to go over. So without further ado, we are going to get started here on aero engines. This is going to be specifically focusing on the 4-stroke cycle and the engine types, and our second class is going to be focusing on engine oil. 4-stroke cycle. 4 parts to that cycle, four strokes to it, but there are a bunch more different components to the engine itself that need to be discussed. So here we have the typical construction of an engine cylinder. I need to turn on my laser pointer here. So we have the piston, which is right here. This is there's mechanical components inside of it that help take energy and convert it that will move up and down. The bore is essentially this this tube here where the piston can move up and down through. We have our spark plug, which is going to ignite the fuel that gets brought into this chamber here. We've got intake and exhaust valves. Pretty straightforward. We have our fuel and air mixture that comes into this chamber here. It ignites from the spark plug, and the exhaust leaves through the exhaust valve. The crankshaft. This diagram doesn't really demonstrate it because it's just a circle there, but this crankshaft is it's a whole rod, and in pistons in a line, they would be responsible for moving that crankshaft along the cams, which aren't demonstrated here, but that's essentially why this is offset from this axle here. So the crankshaft is connected to the propeller, and the sump is kind of like a tray or a dish at the bottom of that cylinder that will contain the oil and make sure that gets splashed up to lubricate components and fulfill the other its other purposes, which we will be discussing in the next video. The cams are, as I said, it's that offset circle. It's got a bit of a funky shape. If I can just pull up my annotation here. So the cam is essentially this part. Oh, I made a mess of it, but it's like this. It's a little bit offset. It's got this, it's a circle with this end that protrudes out, and you can push on that protruding end of that circle to make it spin a little bit easier than if you just had a perfect sphere, because obviously trying to rotate that by just pushing down is very, very inefficient. All right, there we go. So the 4 cycles, we have intake, compression, combustion, and exhaust. Very straightforward. This is a standard engine. Oh, how do I get rid of my annotations? Help. There we go. Okay. 4 strokes of a 4-stroke engine. Intake, compression, combustion, and exhaust. This diagram does adequately show it, and it looks like there's about as many strokes as there are pixels in this image. So here we have our fuel and air mixture being brought into the chamber here. You can see that this valve then closes, and the piston moves up through the borehole and compresses that mixture. The spark plug isn't visible in this diagram, but it would protrude down, and it fires. With this, it pushes the piston back down, and it pushes down on the cam here, which then rotates the crankshaft. And as it pushes back up again, this is going to get pushed out through the exhaust valve. It's just reasonably straightforward stuff here. So we have our induction cycle. So this is the air and fuel mixture that gets drawn inside. So the piston gets forced down by the moving crankshaft, and as this happens, you've got that time for the fuel and air mixture to fill up this space. it's going to create technically a little bit of a vacuum. So as it moves down, there's that empty space that needs to get filled. And so that mixture rushes in to fill it in obviously very carefully prescribed amounts through that intake valve. Then we have our compression stage. This happens when both of the valves are closed and the piston is going to be forced upward through that inertia of the crankshaft. So the crankshaft wants to keep moving, which is obviously on our side. So it's got that residual energy that helps carry it up through another cycle. It comes up and compresses all of this air. And as it gets to its apex, we have the power. So this is when both valves are still closed because we don't want any of that explosive power going out the exhaust or the intake valve. Obviously, intake would be very, very bad because you've got the rest of your fuel and air mixture and you don't want your plane to explode. Generally results in bad days, or so I've heard. And you don't want to just lose energy and have a potentially unsafe detonation that happens outside of this prescribed chamber. So that spark plug ignites the fuel and air mixture when it's at maximum compression, and those resultant expanding gases push down the crankshaft again, and the piston connects with the rod to move it. Lastly, here we have our exhaust section. So this is where the exhaust valve gets pushed open. It's not clearly demonstrated here, but you can see it's out a little farther than our intake one. And as the piston moves up, it's going to push all of those residual gases from the explosion out through that valve. This is a pretty straightforward system, and it works quite well. All right, this I'm just going to kind of go over here. So as confirmation, so match the parts of the reciprocating engine, which is the fancy name for the four-stroke, because each part kind of helps the next. It reciprocates. So as you compress, so the piston goes up in its part of its natural motion and compresses the air. It's got a reciprocating feature in that it helps with the detonation process. So yeah, all right, I didn't put the answers in. I do want to skip through this because there's a lot to this lesson here. So we've got the cylinder itself. We have our crankshaft down here, our intake valve, and our exhaust valve. Our piston is this block right here, so that would be D. We've got the spark plug, which in this case is C. So you can see it's off to the sides. In our other diagram, it was up top. It's not too important as long as it's in this chamber and that detonation happens. E is that connecting rod, and then, as I mentioned, we've got exhaust. Well, I guess according to that arrow there here, this is intake, and then B is exhaust. All right, this is talking about the 4 cycles. You can see whoever created this diagram just used the same one for this here. Anyway. So we want our compression cycle to be where that air is getting pushed up, and we want to have both valves closed. So compression here is going to be part 2. Our exhaust is when our exhaust valve is open. So that's easy to identify. It's right there with the arrow. So 4 is our exhaust. Our intake, you can look for that right there. So we've got our intake where the gases or the fuel and air mixture is being taken into that combustion chamber. And then here at number 3 has got to be power, because that's when the expanding gases are pushing down on the piston to create that next section. So the next part of this lesson is going to be going over combustion engines. There are several different types, and we're going to start with horizontally opposed. Horizontally opposed engines consist of 2 banks of cylinders. So you can see there's cylinders there. They're facing against each other. And then the crankcase is running right through the middle. So this is a flatter design, as it mentions here, and they can fit well into aircraft nose without obstructing visibility or becoming an aerodynamic hassle, becoming a real drag, so to speak. Once again, if you guys were here, I'm sure you would all be in tears laughing at my fantastic puns, so I will just imagine you guys doing that at home. Yeah, they're pretty common in Cessna aircraft, and not just Cessnas, but most small aviation small general aviation aircraft that are used for training purposes. Yeah. Next, we have the radial engine, which has a very big problem of visibility. You see these on a lot of tail draggers. Because it's such a large engine, it's got a very you've maximized its surface area that's facing forward with the propeller. And so because of this, you do find it on a lot of tail draggers. It's always going to have an odd number of cylinders around that crankshaft, and you wouldn't see 1 or 3. 1 for obvious reasons. 3 is just simply not capable of producing adequate power for what's necessary for an aircraft engine. You can often find these stacked behind each other in order to further increase that power. So you can see this here. This is a tad excessive, but you can see that there's, I think, 4 or rather 6, it looks like, of these different radial engines all stacked behind each other. The cylinders are going to fire oppositely, so you're going to have 2 cylinders that fire at one time in order to reduce the vibrations that are experienced. Not just for the comfort of the pilot and the passengers, but also to conserve the integrity of the engine and the aircraft components itself. Because if you've got too many vibrations happening inside of a small space, bolts are going to thread themselves and shear loose, components may break, and you're just going to be subjecting it to a lot more wear and tear than it is designed to take. Inline. So this is what happens where you've got your cylinders all lined up one after another underneath the crankshaft, so or above. So above would be inline, beneath is inverted inline. They result in small aircraft cross sections, so in the nose, but they have very poor cooling because all of these cylinders are compressed together. So you need to get a lot of air into there in order to cool all of the cylinders adequately. So especially you'll see overheating that happens in the middle and toward the end because all of the air that does make it to them has already been heated up. Its cooling power has been used up by those first few cylinders. It also means that the crankshaft is going to be longer and heavier, because if we take this and we compare it to our radial engines here, so it does take up more space, but it's got this many more pistons firing around the crankshaft, meaning that its weight is not as much of a factor. All right, our next section on conformation of the engine types. First of all, we have our horizontally opposed, then we have our radial, and we have our inline. This here, we can see we've got the cylinders are arranged side by side in a row above or below the crankcase, and the small frontal area generates less parasite drag. I'm sure you guys can figure this one out. So above or below is going to give it away as an inline. Even number of cylinders forming 2 banks. Very straightforward again, it's horizontally opposed. Again, less cross-sectional area to generate less drag. And radial. You'll notice the nice thing about these engine types is that they're all very self-explanatory. None of them are trying to trick you with what they should be or what they are.